Okay, so we're now going to use Solver to solve this problem. I just took a little break out to work out how to do a couple of things in Excel. The first thing is I'm going to use the sum product function here, which is a nice way of giving me the product, the sum of the product of each entry in this table times by each entry in this table, which is the total cost. Okay, so if I put here, this equals to sum product times this array, which I can just select, times this array, close brackets. That's equal to 0 because these blank entries here all correspond to 0. So at the moment, we're not shipping any electricity to any cities. Okay, the other thing I'd like to do here is put in this box, I'd like to put in the total amount supplied to city 1. Okay, so that's equal to the sum of these values, is 0. I can drag that across to get the sums for all the other cities, and that's the total demanded. So I'll call that demanded. Okay, so this number has to be equal to this number in our final solution. And in this this box, I can put in here the sum of this row of the total amount supplied by plant 1. And the same for plant 2 and 3. So I can call that supplied. Okay. So now I need to open up Solver and add in the objective functions and the constraints. Okay, so I've done that already in Solver. Let me just delete these and show you what I'm doing. So I'm going to minimize this value here, which is the total cost, by changing these values subject to the constraints. Well, I'd like two sets of constraints to be respected. The first thing is I'd like my supply, so the amount demanded, the total given to each city, to be equal to this number. So I want this number to be equal to, or let's say greater than or equal to. So I'd like city 1 to be given at least 45 units. So I could do that by saying this value, cell reference, has to be greater than or equal to this value. And I could add that in. Okay. Sorry, a bit of a problem there. If I cancel out of that, yeah, I've now got that constraint added in. Now what I could do to keep this, to make this more compact, is to actually add all these demanded constraints in at one go. So let me do that. So I'll add another constraint here, and now my cell reference is going to be all these values, and they all have to be greater than or equal to all these values. And I hit OK there. Okay, so that means that this has to be greater than this has to be greater than this, and so on. So actually I can now delete this single constraint I put in, because this row of constraints covers it. And now I can do the same for the supply. Okay, so each plant cannot supply more than this amount. Okay, so I can say that these values must all be less than or equal to these values. And I can hit OK. So that's my demand constraints and my supply constraints. The final thing is to choose the solving method, what you want to choose for this problem, because it's linear, is simplex LP, which is the standard way of solving linear programming problems. So I've set up my problem, and now I can hit solve. And it comes up with a solution. Okay, so if you see here, the solution has a total cost of 1020 money units, and this is the pattern of allocation. So for example, city 1 has all its demand of 45 supplied by plant 2. And the remaining amount, the 5 units left from plant 2 supply, is given to city 3. Okay, so I can either save those values or I can restore the original values, which in that case were all 0. And I can now illustrate what solution we would get if we just used a heuristic. So there are exact heuristics for this, rules of thumb that can give us the exact solution. But what if we just made one up now? How good could we do? So in the lecture, I discussed choosing the minimum cost link, which is from plant 3 to city 4, and sending as much electricity down that link as possible. So in this case, city 4 requires 30 units, and that can all be met from plant 3 because it has a supply of 40. So in this box, I could put 30, and then that would mean that city 4 don't have to consider it again. It has all its supply met. Okay, now I could look for the next lowest value in these boxes. That would be this one, 6 units, 6 money units to send a unit of electricity from plant 1 to city 2. So city 2 needs 20, so I can meet all of city 2's demand from plant 1. So I can just put 20 in this box here. So we don't have to consider city 2 anymore. Next lowest number is this one, 7, from plant 2 to city 4. But city 4's already had its demand met, so we don't need to worry about that. So we need to focus on city 1 and city 3. Next lowest value on city 1 is from plant 1. So plant 1 could send all its remaining supply to city 1. Plant 1 has 15 units left because it's already supplying 20 to city 2. So I could put on here 15. Okay. So plant 1 doesn't need to be considered again because it's now maxed out. It's sending all its supply to 2 cities. So then looking for the next lowest value, there's plant 2 can send electricity to city 1 with 9 units. So I could send the rest, I can meet the rest of the demand of city 1 from plant 2. So I could put 30 in here. Now city 1's ticked off. We don't need to consider city 1 again. So the final city that doesn't have its demand met yet is city 3. So plant 1 can't meet any demand because it's already sending all its supply. Plant 2 has 20 units of supply left. So we could put 20 in this box because 13 is less than 16. So let's put 20 in this box. And we still need to meet 10 more units of supply of demand to city 3. That would have to come from plant 3. So I'll put a 10 in this box. So satisfied all the constraints. This is a feasible solution. These numbers match these numbers. These numbers match these numbers. So the constraints are satisfied. But you can see that using this heuristic, we get a total cost of 1080. From the optimal solution, we could find a feasible value that was 1020. So that shows you that you can do quite well with rules of thumb. But to get the true optimum, you probably need to use a package like Solver.